Okay, so welcome everybody. I'm gonna, so I wanted to touch base. We're really up to chapter 8 this time at this point. So if you're not through, or at least beginning chapter 8, you're a little bit behind. So catch on up. Those folks who are in the West Virginia class there, we're getting together on Thursday of this week. So you better get through chapter 8 before Thursday. If you're in the Hiram class, you've got a lot more time. So that's good for you. I think that's a week from this weekend, if I'm not mistaken. So you've got a bit. Now, the examination only goes through chapter 8. So it's chapters 1 through chapter 8 is what you will be tested on. But I would like you to finish the last 3, 9, 10, 11 are very short chapters. They'll only take you a few minutes. But if you're preparing and worrying about the certification exam, focus on chapters 1 through 8. As you probably already realized, chapter 7 is the one where you come to reality, that the rest of it was very easy. And then all of a sudden you come to a hard stop and you go, holy Toledo, what's going on here? So that's the one that causes most people. It's sort of where everything comes together. All the other stuff is foundational. And then you start getting into, okay, you got the basics now. Now let's actually design a system. Let's design the wiring. Let's design the array. Let's size the strings, and that's where people start to get a little bit overwhelmed. I don't think any of it is difficult. It's just that there's so much of it and so many things to remember that's where folks run into trouble. Now, fortunately, in the real world, many of these things have become automated. So you no longer have to sit there and calculate the strings for high temperature and low temperature. It's gotten beyond that. Basically, every place requires now, for every building, you're required to have module level power electronics. So you're going to have optimizers or microinverters on the home, and those strings are already calculated for you. So microinverter is very easy. One panel, one microinverter. That's your string. Optimizers, you look up which optimizer I'm using, and in the table from SolarEdge, it says minimum 6, maximum 22. That's it. You have, there's nothing else you do. So all of those calculations are done for you. But you need to understand the concepts behind them. That's why we deal with this stuff. So I've had students in class who have designed solar systems for 5 years. They have no idea if the number is right that comes out of the automated program. They just plug numbers into this thing and it spits out a design. And then they're like, I guess it's okay. I guess that's right. I don't know why it's doing what it's doing. So that's why we need all of this background. Okay. The class times, this Thursday and Friday in West Virginia will begin at 8 o'clock Thursday. All day long, it's labs. So we'll end up 4:30, somewhere in that range. The labs are designed to fulfill all of the requirements of the ETA certification. So there are certain hands-on tasks that you have to have performed in order to become certified. So the labs will perform all of those tasks that are part of that. There are a few other things we do, but you get all of that criteria, and I will check you off that you in fact did it. It's not a, it's kind of a pass-fail thing. You can't do it wrong. You just got to do it. It's like, and we'll keep doing it until you have it right, kind of thing. But it's not like, oh, you didn't connect that, properly. I didn't like the way you held the screwdriver or something. That's not the way that works. Then on Friday, and if you're in Hiram, this is going to be the Saturday, Sunday equivalent. So on the second day, Friday in West Virginia, we'll start again at 8 and we'll begin review. So we'll go through everything that you need to review from chapter 1 through chapter 8, and answer any questions. We'll work through some of the math things. We'll spend all morning long just reviewing the material. And we'll go into the afternoon if people need it, just as much time. At some point, your brain is kind of, this is all that I can absorb and I don't need to keep doing it. Then we'll break for lunch, and then we'll take the exam. So in the afternoon, you'll take the certification exam. The certification exam, you have a 2-hour time limit, unless there's some medical reason that you need longer. Try and arrange that with me ahead of time if you do. Can be kind of almost anything. We're pretty flexible about that. Anxiety, dyslexia, visual, auditory, whatever it is. So we'll give you as much time as you need, but almost never does anybody need even the full 2 hours. It's 75 questions, multiple choice. They're in the same format as the end of the chapter questions. So, in that structure, they're not going to be the same questions, but they're the same type of questions. And I will say that I believe the questions on the exam are not as hard as the questions at the end of the chapters, because I purposefully often try and make the end of the chapter questions a little bit tricky, just to make you think. My hope is you'll miss it, and then you'll try and figure out why. And that's a better learning technique than just getting everything right first try. I also put in a lot of negatives. You'll probably notice that. Which of the following is not? And then I give you 3 of them that are and 1 that's not. I just think that helps you learn, but it's bad when you're taking a test because you can oftentimes get confused. You don't see the not, or there's a negative in the answer, and now it's which of the not, and the answer is this never happens, and you're going, okay, not, never, I don't, So the test will not do that. They will try and word everything in the positive. Which of the following is, which of the following, so everything is positive. Nothing is designed to be tricky on the test. Everything is designed to just be straightforward. Doesn't mean it's easy, but it's not there to mess you up. You've got to get a 75% in order to get the certification. And that means you can miss 18 questions. The first thing people do when they're sitting down to take the test is they go, okay, how many math questions are there on the test? And I'll usually say there are like 8 or 9. So in theory, you could miss every single math question and still pass the exam. But I think I've never seen it where if somebody misses every single math question, they also pass the exam, because they have missed other stuff as well. But don't overly sweat things like string calculations. I would be disappointed if you couldn't figure out how to size a solar array, because that's pretty basic. And the steps to that, just as a review, you take your daily load, you divide it by the hours of insolation. That gets you from kilowatt hours to kilowatts. And then that would be the size of your array if it were 100% efficient, but nothing's 100% efficient. So you divide that by the D rate and you've got the size of your array. So that's really straightforward. One of the things I try and do, I figure if you've done these a few times, the hardest part in doing any of these math equations is, where do I start? Once you're started, then you're kind of on the pathway to sort of puzzle your way through. So with things like solar arrays and battery banks, you always start with your daily load. How much energy am I using in a day? Okay. Then with solar arrays, I want to get from kilowatt hours to kilowatts. So how do I get from kilowatt hours to kilowatts? I divide by hours. What hours am I dividing by? Well, not 24 hours in a day. I'm dividing by the hours of insolation, the amount of peak sunlight. Okay. So that gets me to kilowatts. Now the trick is to remember you got to derate it. Same thing with battery banks. I start with kilowatt hours per day, right? I want to get to amp hours. How do I get to amp hours from kilowatt hours? Divide by volts, right? Watts equals amps times volts. So I take my kilowatt hours per day, I divide it by the voltage of the system, and that's going to give me amp hours per day. Then I need to know how many days, right? Do I want 1 day of autonomy, 2 days, half a day, whatever? That gets me to amp hours. Then I've got to know, okay, I don't use the whole battery. So what's my depth of discharge? So I divide by depth of discharge, and that gives me amp hours that I'm using. And then it says, all right, but the system's not 100% efficient. I got to derate it. But the only piece of equipment between the battery and the load is the inverter. So I'm only going to derate it by the inverter's inefficiency. I don't care about the rest of the system because they're not even in they're not in that part of that I'm looking at. So again, it's kilowatt hours per day, my daily load, divided by the system voltage, then multiply times the number of days, divided by depth of discharge, divided by the inverter's efficiency. That gets your answer. It's really easy if I stand up there and just recite through it. Everybody's like, yeah. But then you're going, okay, how do I get there? So, and another thing that we do with the answers is you can't just randomly keep trying things until you find an answer that matches the one on the test, because we also give you answers that match if you do it wrong. You know, if you forget one step, or if you multiply instead of divide or something like that. So that part's not so straightforward. Then of course, string calculations. That's the one that trips up a lot of folks. Trying to figure out what is the minimum and what is the maximum number of panels in a string. So here again, if you're understanding what you're trying to do, it just really helps in working through the logic of it. So basically, each panel produces a certain amount of voltage. Well, what's the most voltage that panel could produce? Well, that's going to be VOC, voltage open circuit, right? That's the theoretical maximum panel at standard test conditions that a solar panel can produce. Well, if I hook them up in a string, what happens? Voltage increases, amps remain the same. How much does it increase? Well, it's going to increase by VOC for every panel that I'm adding. So at its very core, I would just say, well, what's the maximum voltage of the inverter? What can it handle? I'll divide that by the VOC of the panel, and that'll tell me how many panels I can hook together in a string before I exceed the maximum capacity of the inverter. All right, does that make sense to everybody? If I know the maximum of the panel and I know the maximum of the inverter, how many can I hook together until I've exceeded that inverter's maximum? So that'd be very straightforward, except panels generate more voltage when it gets colder. So how much more voltage does it generate? Well, then I got to look at the temperature coefficient at VOC. So a typical temperature coefficient would be, say, 0.3% per degree Celsius. So then I've got to find the delta. So I'm talking talking them through, and I'm going to go ahead and go to the whiteboard and just write this down, because this one is not as simple. Oh, that's not what I wanted. I don't like the Zoom whiteboard. Oh, I know. It's easier if I screen share. All right. Everybody see my whiteboard here? All right. So if I've got a solar panel, let's say my panel, the VOC is, I'll just pick a number, 36.8 volts. So I'm going to ask some people to help me with this, with the math part. And then the temperature coefficient at VOC is, let's say, 0.26% per degree Celsius. Okay, so I've got to look that up. And I've also got to look up on my inverter. And I find out that its startup voltage is, let's say, 120 volts. And its maximum is 600 volts. Those are pretty common in that neighborhood. 600 is the maximum for a residential anyway, right? Because it's 600 volts is the maximum your system can be designed to. So that's why the manufacturers just say that's the maximum for the inverter. Okay, so I've got those numbers. So how do I figure out what the largest number of these can be hooked up in a string? Well, if I just did what I just said here, I could take 600, divide it by 36.8, and I get how many panels? Somebody with a calculator. You're all on mute, or some of you are on mute.
16.3.
16.3? All right, so I would round down, so it'd be 16 max, right? Except these numbers come from VOC, from standard test conditions. So I know that it will produce more voltage when it gets colder. So how much more? Well, 0.26% per degree Celsius more. So now I've got to look up, or on the test it'll be given to you, the coldest temperature ever experienced at that location. So let's say the coldest temperature, let's pick a place like, I don't know, Syracuse, New York, right? So let's say its coldest temperature is minus 26 degrees Celsius. It's the coldest ever experienced. So what is the delta between standard test conditions and the coldest temperature ever experienced? So minus 26 degrees Celsius, standard test conditions is 25 degrees Celsius. So if we're looking at a continuum here with 0 in the middle here, it's going to be 26 plus 25, or a delta of 51 degrees Celsius, right? Everybody see that? The difference between minus 26 and positive 25 is 51 degrees. So I know for every degree difference, it's 0.26. So I take 51 times 0.26% per degree Celsius, and I get, what's 51 times 0.26? It's going to be around 12 or 13.
13.26.
13.26%, right? So on the coldest day ever, that's going to produce 13% more power, more voltage than it would during standard test conditions, which is where all these have been measured. So now I take my 36.8 volts, which is VOC, times 113.26%, because I'm producing 100%, but I'm producing 13% more. So it's 113. If I want to convert that to a decimal, you just, divide it by 100. So it's going to be 1.1326. And so 36.8 times 1.1326 is somewhere around 40. 43, I would guess.
I have 41.67.
Okay, well, that sounds better. Yeah. Well, what I always try and do is looking at them, I think, okay, 36 plus about 10% is another, 3.5. If it doesn't come out there, I did something wrong, So yeah, so 41.46 volts. So on the coldest day ever, it's going to produce 41.67. Well, now I divide 600 volts by 41.67, and I get,
I'm sorry, I lost you. Somebody else has to answer that one.
yeah, 600 divided by 41.67.
Oh, okay. Actually, do you want to nearest 10th? 14.94.
0.4.
Yeah.
And then
If
we're
I-
gonna round down anyway. So now it's gonna be
Oh.
14 panels max.
Okay.
So that's how you'd figure out your string calculation on the coldest day ever. Is you would just simply do exactly what we did. It's the VOC adjusted for the coldest temperature. And we end up with 14 max. Now, if we want to figure out what's the minimum, so what are the minimum? Well, what we're trying to do here with the maximum, we're saying what's the most panels I can hook together in a string and not exceed the voltage limitations of my inverter on the coldest day ever experienced, assuming there's full sunshine and all of that. Well, that's what we just did. On the minimum, we're saying, well, what's the fewest I can hook up in a string? And it'll still start up the inverter on the hottest day ever. So that we're dealing with the two most extremes. Well, we know that our startup voltage is 120 volts. We got that off our inverter spec. So now we also have to find out what's the hottest day ever experienced in Syracuse, New York. Well, you can go online on Google or whatever and find it. And sometimes you have to convert from Fahrenheit to Celsius because America seems to want to be in the League of Nations along with Myanmar and Liberia as the only two that don't use the metric system. So let's assume that it's 41 degrees Celsius is the hottest temperature ever. Well, once again, what's the delta between those two temperatures? Well, 41 degrees Celsius, 25 degrees Celsius, which is standard test conditions, and that's going to give us 16. Now, here's where I often lose people because we can't just use 16 because it's hotter on a roof than ambient air temperature. It's hotter on the ground. The cells are. If you ever touch a concrete, slab, it's hotter than the air temperature. So how much hotter? Well, the people in the heating and air conditioning people calculated this. And so we have to add 25 degrees Celsius if it's a ground-mounted system. We add 30 degrees Celsius if it's more than, I think it's like 12 inches, whatever, off the roof. So I always say a ballasted system. And 35 degrees if it's a flush to roof. That's the common ones that you see that are just mounted on shingle roofs or whatever. So let's assume this is a flush to roof mounted system. So we take our 16 degrees and now we have to add 35. So now our delta is going to be 51. Just curiously, isn't that's exactly what we had before, right? 51 degrees. So the delta is 51 degrees on the hottest day. But in this case, we want to err on the low side, not on the high side like we did before. So we don't use VOC, we use VMP, which is the operating voltage, not the theoretical maximum. And then we use the temperature coefficient at VMP. And oftentimes that will be shown as temperature coefficient at Pmax. Those are the same numbers. So when you look up on a spec sheet, it doesn't really matter because you're at VMP when you're at Pmax, right? That's the voltage. So these numbers are always going to be a little bit lower for the voltage. So VMP, if the VOC was 36.8, let's assume this is going to be 32.9 volts. And the temperature coefficient is always going to be a little bit higher because you're starting at a different point. So let's assume this one is 0.32% per degree Celsius. So we get those from the solar panel spec sheets. I'm just making them up for this example, but we get them off of a sheet. So I take 51 degrees times the temperature coefficient. So it's going to be times 0.32% per degree Celsius. So what's 51 times 0.32?
16.32.
16.32. So in this case, it's telling us that on the hottest day ever, this panel is going to produce 16.3% less voltage than under standard test conditions. So I take my VMP, which is 32.9, and I'm going to multiply it times 100% minus 16.32%, because it's producing 16.32% less. Or this is going to be 83.68%, right? Did I do that right in my head? Or if I decimalize it, it's going to be 0.8368. Hopefully I did that right, because otherwise I'll confuse everybody. All right, so I take 32.9 volts times 0.8368, and I get I would guess somewhere in the neighborhood of 26, 27, somewhere in there.
27.53.
27.52. 3 volts. Not that that's going to matter. All right. So on the hottest day, that panel's only going to produce 27.5 volts. Notice the difference, right? 41, almost 42 volts on the coldest day, 27 on the hottest day. All right. So what do I divide that into? It's my inverter startup voltage. So if my inverter starts at 120, and on the hottest day, I'm only going to produce 27.53 volts, that's going to give me 5, right? 4 point something. What is it? 4 point?
I'm sorry, I got distracted, so I didn't do it.
Uh-huh. Well, you're the only one following through. Everybody else is riding on your coattails. So
What was I supposed to?
120 divided by 27.53. I know it's going to be 4 point something.
4.358.
4.358.
Yep.
Okay, so we'd round up 5 panels max or minimum. Okay, so our string calculations based on what we know, which is the solar panel that we've selected, the inverter that we've selected, and the city that we've selected. Our strings have to be 5 panels minimum, 14 panels maximum. So that's what we've taken away from that. So if we have a solar array, let's just say our solar array is 30 panels. Fairly typical size residential system. So we've calculated the size of this system as 30 panels. How would we best configure this? Well, for a string inverter, they've all got to be, every string has to be uniform. I can't have one string 14, another string 14, and 1 2. You know, I've got to have them balanced. So in this case, I'd probably go with 3 strings of 10. Very logical, very easy to deal with. I can't do 2 strings of 15. If I could, I would, but I can't because it's 14 max. You want to try and minimize the number of strings if you can, and you want to try and get as high a voltage as you can. So really 3 strings of 10, that's going to be our configuration. Everybody clear on that? So that's about, I would say this is like the hardest math question that's on the test. you don't do these string calculations very often in the real world, because we've kind of gotten out of these straight string inverters. We've gone to really microinverters and power optimizers. So it's very rare that you're going to be dealing with string inverters like this. The only time would be if you're doing a ground mounted system. And then you might find a low cost option where that would be your thing. All right. So I kind of jumped into that with the math thing. Does anybody have any questions? Because this is kind of for the group in West Virginia, this is your last shot. The people in Hiram will have another shot next Tuesday. But so anybody have something they ran across while you were studying that you were just a little bit confused about?
Jay, I did have a question on, you were walking through how to determine the battery bank by converting the kilowatt hours per day, dividing that by the volts to determine your amp hours per day.
Yeah.
And then you said you divide that amount by the depth of discharge, and then you derate it by the inverter's inefficiency only. I
Yes.
guess what I get a little confused about is when I consider, if I'm using lead acid batteries and I consider the round trip battery inefficiency, is that only factoring into when I determine the size of the array, not the battery bank itself?
Exactly. Yeah,
Okay.
because the round trip inefficiency is basically saying for every 100 watts that I put into the battery, I'm only going to get 75 watts out. But the amp hour capacity of that battery is already telling you what you're getting out. So yeah, it may be inefficient in converting energy from solar to battery power, but I know what that battery power is. So the only thing that's throttling me down between the battery and the load is the inverter. So for instance, let's say that we have we'll just do a little standalone example. So we've got our little cabin in the woods, and we've done a load assessment because it's a standalone thing, a load analysis. And let's say that we've just decided, trying to think something realistic, it's going to be 8 kilowatt hours per day. Okay. So that's the usage of everything that we're doing. 8 kilowatt hours a day. And we've gone on to PV watts. And at this location with this orientation, we've found that it's 3.98 hours per day of irradiance, of insolation, right? Everybody with me so far? So we did that, a load analysis that got us that number, and PV watts got us this number for this site. Now I've decided that I'm going to use a standalone system because this is a hunting cabin out in the middle of some mountaintop in West Virginia, right? Maybe, or instead of a hunting cabin, let's just say that I've decided I'm going to quit my corporate job and move to a mountaintop and avoid technology and stick it to the man and live my life, raise some dairy goats, plant an organic garden. Okay, so this is where I've decided to go. All right, so next I need to know, well, what size array? Well, I'll have to kind of figure out my system. So I have to derate the system. So let's say that there's what are the main derate points? Well, the inverter. The inverter is one, and let's say that's 95% efficient, the one I picked. I know I've got voltage drop, and we always sort of throw a 2% number in there for voltage drop. Now I'm going to also put in connections, terminations, whatever, and I usually just put in like 1% for that. Then maybe we just add a percent for soiling, it's going to be dusty or whatever, so that's 1%. Then batteries, let's say that this is going to be a 20% inefficient. So they're only 80%. I should probably, I'll say 20% inefficient. The inverter is only 5% inefficient. Okay. So round trip efficiency on lead acid batteries can be as high as 25% off. So put in 100 watts, you only get 75 watts out. So I'm going to say it's 20% inefficient. And then because this is a standard string inverter system, then I might get a plus or minus 5%. Like if a panel is like made on a Monday, maybe it's 5% less efficient than a panel that's made on a Wednesday. It's the same panel, but you'll see oftentimes in the spec sheet, it'll talk about power tolerance. So let's say that the power tolerance is 3%. So the panel itself can vary in output as much as 3%. And you'll see that this does in fact happen, especially if you're monitoring a microinverter system where every panel is showing independently. Some panels just work better than others, slightly better. With a microinverter system, it all balances out because everyone's operating independently of everyone else. So some are better, some are worse, and it all balances out. But in a string inverter system, they don't. The worst case is what you end up with. So we're going to go with a -3. So let's just say we've derated that. We've added all these together and we came up with 25, 30, 32. So 32% inefficient. So far, this isn't looking good. So my D rate is going to be 68. D rate. So it's only 68% efficient for this standalone system. So now I think I've got the numbers I need to size my array, right? 8 kW per day divided by hours per day, 3.98 hours per day. The hours per day cancel out. So what's 8 divided by 3.98? It's going to be 2 point something, right? 2 and a fraction. Somebody give me a number.
2.01.
2.01. Or I'm going to convert this to watts, 2010 watts instead of 2.01 kilowatts because it's a small system. All right, so that's the size of my array. Well, notice that the battery round trip inefficiency has been factored in here. Okay, so now I want to size the battery bank. Well, let's say that I decide, and I use this as an example a lot because they're cheap lead acid batteries. They have from Trojan a 6-volt, 250 amp hour battery. Okay, those things you can buy for like 125 bucks. They're golf cart batteries. They're deep cycle golf cart batteries. In fact, if you live near a golf course, maybe you can get them for free in the dead of the night, right? You just go out there and find their golf carts and make a run for it. Some of these places you can actually, like country clubs, you can make a deal with them and buy them because they replace them every year. So they don't want a problem. So they just take perfectly good batteries and, recycle them because they're wanting new batteries every year. Same thing with airports. You can buy aviation deep cycle batteries because the FAA requires they be changed out every year. So if you've got a small private airport nearby, you might do a deal with them to just say, I'll buy for core charge. Core charge is basically the recycling charge. So I'll buy these batteries from you for core charge rather than you take them down to the recycling and get your core charge. So good deal. All right, so this is the size of our array. So what's the size of our battery bank? Well, we start out our daily load, 8,000 watt hours per day, 8 kilowatt hours per day. And our system is going to be 48 volts. And that gives us
166.66.
366.66 amp hours.
I'm sorry, 166.
Oh, one. Oh, okay. 166.66.
Mhm.
Okay. Well, are we done? That would tell us the amp hours per day if it were 100% efficient and we could use the whole battery. So we can't use the whole battery. Well, first off, I usually say, well, how many days of autonomy do I want? So let's just say that this is a place I'm living in the woods, and I want 3 days of autonomy just because I do. So I'm going to take that times 3. That's going to give me right at around 500.
Yeah, 499.98.
499.98, or close enough to 500 amp hours. All right. Are we done? No, because this assumes 100% efficiency, and it also assumes we're using the whole battery. So because
Jay, I
I'm
have a question real quick, if you don't mind.
yeah, go ahead.
Sorry, I don't even know if I missed it. Where did the 48 volts come from? What is that?
Oh, yeah, it's the system configuration I decided.
Okay.
My system, and most residential housing systems standalone are going to be 48 volt. It's really now a matter of, for very small systems, they might be 12 volts. You really only have a choice between 12, 24, 36, and 48.
Right.
Almost
okay.
nobody
I didn't know
uses.
if it was like some math I missed somehow.
Oh,
and I was looking.
no, that's
Okay,
good.
cool.
Good catch. Yeah. Most of our systems are 48 just because that's the reason, that's the highest we can do. Why are we limited at 48? It's because the National Electrical Code says for battery systems in a home, you cannot exceed 50 volts, right? Why did they pick that number? You'll have to ask all of the middle-aged white guys who get together at these meetings at Jackson Hole, Montana, and Honolulu, Hawaii, and try and out engineer each other. So I used to attend some of these type of meetings, and oh my God, you never saw so many pissing contests in your life. But they're mostly manufacturers reps too. Because the manufacturers are the ones who can afford to send these people to protect their turf. That's really all they're doing at these standards meetings, and is saying, don't let them do anything that's going to affect our profitability next year, kind of thing. That's if you ever wonder why standards and codes are so messed up, that's really why. And plus it's a consensus model. So you got to have 100% agreement pretty much. Otherwise it doesn't move forward. So you get a lot of weasel words, a lot of, could or should instead of shall. Okay, so all right, we're here. 3 days of autonomy, but we can't use the whole battery, right? So the whole battery, we're going to say, let's do a 50% depth of discharge. For a regular standalone system, that's pretty average. I could do 90, if I want the batteries to wear out faster and use less battery, or I can use 50. So in this case, if I divide this by 50%, it's the same as multiplying it times 2. So for ease, I'm going to say it's now 1,000 amp hours. Right? I just converted this to 500. Everybody see that? So this is the depth of discharge. Then the last thing I have to do is divide this by the inverter's inefficiency, or the inverter's efficiency. So I divide it by 0.95. And it's going to be 1,000 and some change. 1,050, is that right? Maybe somewhere in there.
Yeah, 1,052.63.
So our system now has to have 1,052 amp hours of battery. Okay, so how many batteries do we need? Well, each battery is 250 amp hours. So I could go with 5 strings of batteries, Or I could look back and say, well, 3 days was somewhat arbitrary. Maybe I'll go with 2 days and a little bit, less than 3. So I would probably come back and say, let's just go with 4 strings. It's close enough to 1,000. So I'm going to have 4 strings of batteries. I could go with 5, but I'm going to go with 4. And I'm especially going to go with 4 once you see the price tag on this. So I need 4 strings. And how many batteries in a string? It's a 6-volt battery and a 48-volt system.
Eight.
8 of them. 8, right? Because 8 times 6 is going to get me to 48. So 8 in each. 4 of them. So I'm going to need 32 batteries. Times by $125 for each one. So that's going to take me to
$4,000.
more than that. 4,500. Is that right?
Oh, wait a minute.
No.
Maybe I messed up.
Oh no, 4,000. You're right. $4,000.
Oh.
Yeah, 4,000 exactly. Okay, so that's the cost of the batteries. If I wanted to figure out my solar panels, this is 2,000 watts. So let's just say that I've got 250 watt panels. That's going to be 8 panels. 8 panels is in the neighborhood of, say, $200 a piece, to be generous. So that's going to be about $1,600 for the panels. My inverter, it's going to be, well, what size inverter will I have? What is that based on in a standalone system? I'm going to jump out of this screen. Can I leave this screen, or does anybody need to see it?
Before you leave, I did have a question, Jay. Sorry.
Sure.
We went through this exercise of documenting the various components that were going to derate the system. We came up with 32%.
Yeah.
Derate. Well, I guess it's 68% derate.
Yeah.
But we started from the assumption this was an 8 kilowatt per day array.
Yeah.
So is this implying that the 68% derate was already factored in when we determined the 8 kilowatt per day array size?
Oh, you know what? I think I missed a step, right? I need a bigger array because this would be an 100% efficient array, right?
Right.
So now I have to divide that by 0.68.
Okay, that makes more sense. Okay.
All right, sorry about that. So what is that? Well, it's 2/3 of that. So what is it going to be, about 3?
3, yeah.
So now I need a 3 kW just because my system's only 2/3 efficient. Yeah, so that's a good catch. So my panels, instead of this, it's going to be more like $2,400 for my panels. Okay.
Okay, now
Well,
let me ask one more follow-up, because it seems like we included the inverter inefficiency on the front end. Do we
Yeah.
still factor that in when we're determining the battery efficiency? Okay.
Yeah, we do it twice. And the reason is because basically we're saying, okay, our panels have to generate all the power I need, and that includes to the load.
Yeah.
And our batteries only have to generate the power I need from the battery to the load. But where I'm starting is what they rated it at.
Right.
So that's what I'm derating from. I'm just
Yeah.
saying, okay, you said if it's 100% efficient, but it's not. But that inefficiency applies not only to the panels, but it also applies to the battery, only because I'm using a number they provided me. If I were, it's not like wiring size where I've derated it and it keeps following down the line. it's basically because I'm starting with their idea of a perfect world and
Got it.
adjusting from there.
Okay, good, thank you.
Okay, so this is an important concept here, and I'll finish it up with this. I asked you, how do we size the inverter in a standalone rate? And this really sounds like two questions on the exam. So I'm going to draw a standalone system. So the first part is the array. What's the next piece of equipment we connect to? I just want people to shout out. So where did we go from the array?
Connector box or junction box?
Yeah, the junction box or the combiner box.
Yeah.
So then from the combiner box, we go to
Disconnect.
a
DC
disconnect, the DC disconnect, right? We're still in DC system. From the DC disconnect, and again, this is standalone.
To another DCD.
You might have a second DC disconnect. We'll just conceivably not have that in this, but there could be one at the array and there could be one at the house. That's very common. So what's the next piece of electronics?
Charge controller.
Charge controller, right? And what does the charge controller do? Controls the charge from the array to the battery, right? Okay, that's all its purpose is. Now, what's next?
Inverter?
Inverter, right? We need to convert from DC to AC. From here,
AC disconnect.
yeah, and in a standalone system, often the AC disconnect is your main in the breaker panel. You don't have to have one out at the meter because there is no meter. You know, so as long as you can turn it off, and it's usually just the main breaker in a distribution panel. So this would be your very simple system. You might add a generator that connects into the inverter. It just connects into a port there and is controlled by the inverter. But this is the basic. All right, so the question I had is, what determines the size of the inverter? And I should also point that from here, we're going to loads. Well, the important thing to understand is this system could be dissected right down the middle of the battery. The battery is this sort of transition point. All of the loads are powered from power that's being pulled from the battery to the load. And all of the power in the array is used to charge the battery. Neither side worries about the other side. You know, I could have a system that doesn't even have an array, and it would work until the battery runs out of power, right? Then it's dead. Or I could have an array that just charges a battery and doesn't power anything, and it would work until the battery's full. But in tandem, the array is charging the battery and the battery is powering the loads. And you try and size the array so that it recharges what you use each day on average. Otherwise, if you were too small, it would gradually run out of power and eventually be dead. If it was too big, you'd simply be building a system bigger than you need. All right, so what determines the size of the battery or the inverter? It's the maximum power draw. Whatever the maximum amount of power that can be driven by the loads at any 1 second, your inverter better be big enough to handle it. Otherwise, it's going to act like a tripped circuit breaker, right? You've tried to pull too much power through it. It has nothing to do with the array at all. Could care less. Could care less if there's an array. Conversely, in a grid-tied system where we don't have a charge controller and we don't have a battery bank, We have an AC disconnect here, and then we have the grid. Well, what happens with loads? If I pull loads, what happens if I'm pulling more load than my array can handle? It just gets subsidized by the grid. What happens if I'm producing more power than I need? Well, it goes to the load first, but then it goes out to the grid. So what's happening? Everything my array is producing is going through the inverter, independent of how much I'm using. I don't care what my load is. So the only thing that determines the size of my inverter is a relationship between the array and the inverter. So I'll leave you with that because we're out of time, but just understand standalone system, the inverter size is based on power draw, and a grid tied system, it is a relationship with the size of the array. Doesn't have to be the exact same size, but it is a relationship with the size of the array. Okay, we'll touch more on that when we do the review, or even next week if you have more questions on that for the Hiram people. All right, so I'll talk to you guys later. And if you have any questions between now and the test on Thursday, or the lab on Thursday, or the lab a week from Saturday, get back to me. All right, take care. See you guys
Thank
later.
you.